In this section, we're going to learn how to do curve sketching. So what I want to make sure that you have with you um, are number one, your curve sketching template. So we're going to fill out information in here. So this is kind of a long process, but we'll follow through as best as I can show you. And also, again, there is a grid down here. I may graph on this because it's a little bit bigger, but we're going to fill out most of the information going to here. So I'm going to be kind of flipping back and forth and explaining why I do different things. So the first thing that we want to kind of figure out is looking at our original function. So we're going to kind of start here with f of x, or in this case, that we have h of x. So it asks us to figure out what the zeros are. So this is going to be a pattern for a lot of stuff. So we're going to try and figure out everything we know about this graph based on its original function. Okay, so h of x equals this. So one thing that I want to know is I want to know the domain. So I need to try to figure this out. So that kind of tells me, how long is my graph going? Is there anything weird happening? So this is actually a polynomial that's factored. So x minus 1 cubed times x minus 5. So it's a fourth degree polynomial. So this is, since it's a polynomial, it's going to be all real numbers. Our range we don't really know yet because we haven't really found our maxes and mins, but this is a good piece of information for us. We can figure out our x-intercepts. So our x-intercepts are going to occur when h of x equals 0. Okay, so we have our equation x minus 1 cubed times x minus 5. We're quite lucky with this because we already have this factored. So what I know based off of this right here is that there's two possibilities. Either x minus 1 equals 0 or x minus 5 equals 0. So either of those has to happen for x-intercepts, which means that we're going to have x is going to be either 1 or 5. So I know that those are going to be x-intercepts of my graph. We can also figure out our y-intercept. So our y-intercept happens when x equals 0. So okay, so sorry about that. So what we do is we take h of 0, and so that's going to be 0 minus 1 cubed times 0 minus 5. That gives us negative 1 cubed is negative 1. We multiply that by negative 5, which gives us 5. So we know that our y-intercept is going to be at y equals 5. So these are all the things that we know about this from our original function. Now there's some other things that we can kind of figure out when it comes to called like end behavior. So knowing that this is a fourth root function, fourth root functions are kind of like parabolas in a way. So if you think about it, like I'm going to draw here like a line kind of starts in one direction, ends in another, and then you have a parabola. So parabola starts in one direction and starts going down and then goes up, or it starts going up and then goes down. Cubes can either be like start going up, start going down, and then kind of it follows this pattern over and over. So this is a fourth root function. So we're going to fill out the information in our template based upon what we've seen here. Okay, so our zeros we found, those are our x-intercepts. So the zeros of our original were our was x equals 1 and 5. We found out that our y-intercept is 5. We know our domain is all real numbers. We have so end behavior down here in the bottom left. If it's a polynomial, the leading coefficient is going to be 1 here, and we know it's a degree of 4. So the leading coefficient, again, kind of comes back to if we were to multiply this out, we would end up with 1x to the fourth. You could multiply that out, but you can kind of see how that would work as well because there's no numbers attached to the x's. And we know it's a fourth root function. So basically what this is going to mean is like when x approaches negative infinity, y approaches infinity. And when x approaches infinity, y approaches infinity. So it's basically going to look kind of like a u or a lumpy u. Okay, so that's about all the information we can tell right off the bat about our function. So we know that this was, x minus 1 cubed times x minus 5. So what we're going to do now is start to fill out more information. So we're going to go to f prime now and start kind of basically do the same process again. Oops, sorry, I'm getting all messed up. So when we do h prime for this, we have to do the product rule. So we're going to do h prime of x. It's going to be the derivative of our first term, which is 3 times x minus 1 squared times 1 from the derivative of the inside. We multiply that by our second function, and then we add on the first function times the derivative of the second, which is just 1. So we can kind of clean this up a little bit. We can get 3 times x minus 1 squared times x minus 5. And then we add on x minus 1 cubed. So this is h prime. This isn't a very useful version of it, so we're going to want to do something. We're going to want to factor this, and it's going to make it a little cleaner, easier to look at. So the one thing I see that we have in common are the x minus 1s, and so I'm going to rewrite this as 3 times x minus 1 squared. Now, what's left inside of here is I have an x minus 5 from the first term, and then I'm left with an x minus 1. Now, technically, these are both in parentheses, but because I'm adding them, I don't need it. Which, at the end of the day, is 3 times x minus 1 squared times 2x minus 6. So this is a factored version. Very, very helpful when we're trying to figure some stuff out. So we can figure out a couple of things real quick, like what are our critical numbers? Well, if our critical numbers, we do h prime of c, and that's going to be 3 times c minus 1 squared times 2c minus 6. So when are these equal 0 or undefined? Well, it's not going to be undefined because this is still a polynomial. So it's only going to be where we have c to equal, or our h prime equal to 0. So it's either going to be when c minus 1 equals 0, or it's going to be when 2c minus 6 equals 0. And we should find that we've got c to be 1 and 3. So what we kind of want to do with this, all right, and I'm going to kind of erase this top section here. What we're going to do with this is now try to figure out, well, what is going on in this period of time? So what is happening before 1, after 1? So I'm going to do my first derivative test. So I've got the points 1 and 3, and so I need to create some test points. So my test points, I'm going to use 0, I'm going to use 2 and 4. So I want to know what h prime is at those places. So h prime of 0, and again I can use my factored form that's down here, is going to be 3 times 0 minus 1 squared times 2 times 0 minus 6. So that's going to be 3 times 1 times negative 6, which is negative 18. Mainly what I care about that is that it's negative, right? So that means that up till 1, my graph is decreasing, right? That makes sense based on the picture that we had earlier. So we want to confirm what else is going on. So we got to do h prime of 1, or excuse me, 2. Right, I can't use the critical number. H prime of 2, so we get 3 times 2 minus 1 squared times 2 times 2 minus 6. And that's going to give me 3 times 1 times negative 2. So that's negative 6. So very interesting thing that just happened there is that I still am decreasing. So we know that 1, x equals 1, is not going to be a minimum like we might have thought before. So that's actually going to be an inflection point likely. So then we're going to go to h prime of 4, and we're going to get 3 times 4 minus 1 squared times 2 times 4 minus 6. And so this is going to equal 3 times 9 times 2, which is 54. So we know that this is positive. So let's go in and let's start putting out stuff that we know about our graph. All right, so let's take this information. Okay, so we've got, again, we had this was 3, oops, I'm going to use the other pen, sorry. We've got 3 times x minus 1 squared times 2x minus 6 was the first derivative. We have equals 0 when x equals 1 and 3. It does not exist. It doesn't matter. It doesn't exist anywhere. We know our intervals of increase and decrease. So we've got 1 and 3. So we know it's negative, negative, positive. Very good. So we know that that's excellent. Now we know that we're going to have a minimum when we have x equals 3. Now we know that because if we look at 3, we go from an increasing or decrease to increase. Okay, so it's x equals 3, which means that the point there, if we go back to the original equation and kind of plug it in, so look back at over here in the top left box. So we would have 3 minus 1, which is 2. We cube that, we get 8. 8 times negative 2, which is 3 minus 5. So 8 times negative 2 is negative 16. So that's our minimum. So our graph doesn't go lower than that. And we know that based on our end behavior and some other things. So good. So we've gotten some extra pieces of information. All right. So now we're going to go and do the very last thing, which is deal with our second derivative. So we knew that h prime of x was 3 times x minus 1 squared times 2x minus 6. Okay, so we're going to go ahead and find h prime, or h double prime. So h double prime, now what we're going to do is I'm going to split this again into 2 separate ones. Okay, so I do its product rule again. So I'm going to get 6 times x minus 1 to the first times 1, and then that's times 2x minus 6. I'm also going to add on, so the first function, which is 3 times x minus 1 squared times 2x minus 6. Okay, so we've got that piece. Oh, no, I'm crazy. What am I doing? It's just 2. Right, so we've got just 2. So we're going to clean this up just like we did last time. So we're going to have 6 times x minus 1 times 2x minus 6 plus 6 times x minus 1 squared. Okay, so we could multiply this all out and kind of do that, but I'm going to factor this kind of like I did the last one. So I'm going to get 6 times x minus 1. So I'm going to factor that out of both of these. I'm going to be left with 2x minus 6 from my first term. I'm going to be left with just a single x minus 1 left over in the second because I've already pulled one out. Now again, technically these have parentheses, but again, I don't need them because I'm adding these two guys together and I'm not multiplying them by anything. Okay, so this can simplify to 6 times x minus 1 times 3x minus 7. Okay, Wunderbar. All right, so we've got h double prime of x is 6 times x minus 1 times 3x minus 7. Okay, so that is going to tell me, this is going to tell me about my concavities. So like when am I a U, when am I not? So we can kind of, or when am I a U, when am I a hill? We're going to kind of go forward from there. So I'm going to erase this section so that I can do my concavity part. Why did my circle seem to get smaller here? Okay. So based on that, doing the same thing that I did before, doing my line. Okay, and so I need to find where my possible points of inflection are, which that happens when my second derivative equals 0. Well, like before, since it's factored, it makes it nice and easy. So we get 3x minus 7 equals 0, either one of those two. So we know that our possible inflection points are either going to be at 1 and at 7 over 3. So we're going to do the same thing that we did before. So we're going to get 1, 7 over 3. And I'm going to pick some test points. So 0 is always a good one. Between 1 and 7/3 is the number 2. And then after that, we'll just do 3. Make it nice and simple. So we go back and we're going to say, okay, well, what's h double prime of 0? So this is going to tell me the concavity in the first section of the graph. I could almost guarantee you that it's going to be positive. Right? So because of the way that I know this graph is shaped. It's kind of like a parabola if you think about it. So you get 6 times 0 minus 1 times 3 times 0 minus 7. This gives me 6 times negative 1 times negative 7, which should be 42. Right, the answer to the life, the universe, and everything. This is positive. Okay. And we've got h double prime of 2. So we're going to plug this in. We're going to get 6 times 2 minus 1. And then this is 3 times 2 minus 7. Okay. And so we get 6 times 1 times negative 1. So this is negative 6, so we get a negative section. So we do have an inflection point at 1. Makes sense because we had it as a critical point as well, but we didn't change concavity there. And then lastly, we've got h double prime of 3. This should be positive again, so we get 6 times 3 minus 1 times 3 times 3 minus 7. And that's going to give us 6 times 2 times 2, which should be 24. So it's positive. So this tells me some more information. So I'm going to copy this over. So we've got 1 and 7/3 are these possible points. These are inflection points. And so we're going to go back. Whoa. Okay. So we've got, switch colors again. We've got 1. We've got 7/3. And we know it was positive, negative, positive. So we've got points of inflection are when x equals 1. So again, we can plug that into our original function. 1. If we plug 1 in, it's going to zero out that x minus 1 cubed, so it's going to give us a 0. And then, again, we're going to have, it's when x equals 7/3. That's a little more complicated. Okay, so 7/3 minus 1 is 4th, so 4/3 cubed. And then times negative 8/3. So 64 over 27 times negative 8 over 3. Good Lord. That's crazy. And it doesn't work out very well. Why? So that's a crazy point. I'm going to just kind of estimate this a little bit because this is kind of a toughie. So this is basically this is a little, it's almost 2.5, and then this is almost negative 3, so it's about negative 10, I'm guessing, or no, not negative 10, so 2.5 and negative 3, so we'll say like it's negative 7. We'll say it's negative 7-ish. It's not really good math there by me, but good enough. Okay, so we want to start putting that information together. So 6 times, whoa, 6 times x minus 1 times 3x minus 7. We know that we had those equals 0 and x equaled 1, and it's 7/3. And so at this point, we've done a lot of work, and so we have all the information that we need to go forward. So let's start putting down the points that we know that exist. Okay, so I know that my first thing is that I've got x equals 1 and 5 are my x-intercepts. So let's go to x equals 1 and x equals 5 are my x-intercepts. Perfect. So I know that my y-intercept is at 5. So I can go back to that and do my 1, 2, 3, 4, 5. So I know that that's there as well. Okay, very good. Oops. I know that I have a minimum at 3, negative 16. Okay, so that I do not have the ability to do that on this graph. So I'm going to do these as 2's to make it a little simpler. Now the x's are still x. This is 1, 2, 3, 4. So I'm just scaling this a little bit different. And we don't go any lower than that. So I know that we've got that. So it's 3, negative 16. Perfect. So you're starting to see kind of this graph take shape a little bit. So one of the other points we know, I know that I've got a point of inflection at 1, 0. And I also have a point of inflection at 7/3 and roughly negative 7. So I know this is a point of inflection at x equals 1. And I know that my other one is at 7/3, and so that is just a little over 2, and then about negative 7, so it's right about there. So this graph is kind of funky. So remember, we're decreasing first, so we go down, so we're decreasing, and we have a positive concavity. So now at this point, it switches to have a negative concavity, so it starts diving faster. But then it switches again. So in a sense, all of the pieces of information we need for a graph can come from analyzing the function of what f is, of what f prime is, and also of what f double prime is. So this one, there's only one place where the slope creates a critical point, really, that makes a min or a max of any kind of extrema, and that's down there. The other impactful points are going to be our points of inflection and our intercepts, and so we can kind of draw our graph. Now, this would work fine. Mainly, you're just getting the right idea that things they kind of change and how to draw them. So big time, this is going to be useful for us to kind of put everything together, and then at the very end, we kind of sketch our graph.